All right, everyone. So in this objective 102, you've been reading about protocols and technologies that are specific to the data link layer, and they want you to be able to explain those and understand the concepts that all relate to the data link layer. The primary one, the first one they want you to dive into is explaining the purpose and functionality of a MAC address. Now, it mentioned earlier that you should understand addressing at each layer of the OSI model and the different types. This is one of the types. MAC addresses have given us the ability to identify a node on the wire uniquely, much like an IP address at layer 3 does. A MAC address is a physical address of a network interface card. The manufacturer controls that space, that IP or that MAC address space. You'll see them; they're unique to each interface. So if you have a PC or a system node on the wire has presence on the network, that node should have a MAC address that's unique to that node. That does not mean there isn't such thing as a duplicate MAC address. And if you've ever seen a duplicate MAC address in your networks, you should have taken a picture because it's a pretty rare thing. But if you've ever seen one before, they are a 12-digit address, much like the one you see below here. And they can be annotated in different ways. So here we have a 2-digit colon, 2-digit colon, 2-digit colon style MAC address or annotated MAC address. You'll see these different ones in different operating systems, different ways of looking at it. Another way to see this same exact MAC address in a different operating system, they may be annotated in this pattern where it's a 4.4.4. And you may also see it even further along. You may see it in a different format of a 2-2-2- type of a format. The first 6 digits are representative of the manufacturer of the NIC card or the interface, and the last 6 are unique to that individual interface. The second one you see here in the presentation, the 4.4.4, is actually typically used in routers. So if you've ever gone into a router's ARP table, perhaps you've seen this type of an entry of a MAC address in the ARP table. However, in Cisco routers where you would see this type of a format, if you went into a Cisco switch back in the day, let's say way back in the day, we're talking like the 90s and the early 2000s, you may have actually seen it in the format that's on the bottom of the list, in the 2-2-2-2, and that would have been Cat OS stored its MAC addresses in that format. So MAC addresses can occur in many different formats, but just understand it is a unique identifier of a node on the wire, and it may turn up in a couple of different formats. As you can see here, I'm showing you an output from a Linux or Apple based operating system, and the MAC address is called an Ether address. It's not called a MAC address, it's called an Ether address, and that one is a 2-digit colon, 2-digit colon format. And if you look into a Windows operating system, you may see that when you show the network connectivity or connection detail, you may go in and see that it's a physical address. It's not actually called an Ether address or a MAC address. It's called a physical address, and it is a 2-2-2 format. So, like I said, different operating systems represent it differently, maybe even call it different things, but what a MAC address does is it allows us to uniquely identify a node on the wire at layer 2. All right, our next objective point is going to be to explain the purpose of a switch's forwarding database. Now, when it comes to switches, layer 2 based devices, we should all be familiar with a switch as a layer 2 device. But there have been other layer 2 devices prior to switches in the industry. Before switches, all layer 2 devices are known as bridges. If you've ever heard the term a bridge, a network bridge, that would be a layer 2 device, which would be similar, would basically be a switch. But you may have heard of the term a hub. So if you were, cutting your teeth in the network like I was in the 90s, coming out of Token Ring and moving into Ethernet, we had hubs before we had switches. And basically, a hub, the difference between the two, was that a switch was more intelligent than a hub. A hub was like expanded wire, if you want to think of it that way, where if a packet came in headed for some other system, the hub was not intelligent enough to know what to do with the packet specifically. So what it did was, as a packet came in on interface 1, let's say, he would send it out all other ports, not back out the same port he received it on, but out all the other ports. So if it was a 16-port switch, he would receive a packet in on one interface 1.1 or interface 1, and he would send it out interface 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15, and 16. So a lot of replication of data being sent out to all ports, because he didn't know where it was destined for, so he had to get it to everywhere. This creates an overhead or a burden on the network, in that if you have a packet coming in and it's being sent to everyone on the wire, every single operating system on the wire would have to stop what they're doing, because the packet just came in at layer 1. Remember, I told you guys to visualize the operating system of a node, much like the OSI model. They would have to take that packet in on layer 1 on their physical connection and say, is this packet for me at layer 2? Is it destined for my MAC address? And if it isn't, they would then throw it away, Bitbucket the packet, and go back to work. But of course, in a hub environment, every single packet that flies goes to every one. So it was constantly being interrupted, saying, is this for me? Nope. Is this for me? Nope. Is this for me? Nope. And finally, when he would get one that says, is this for my MAC address? And it is for my MAC address, then he would hand it up to layer 3 and say, is this for my IP address? Should I be dealing with this? And it would go through its full path through the operating system to then respond to the packet and send a packet back out. And of course, that packet headed back out would go out to every single device in the network, not just the one it was destined for. So hubs were not intelligent. They did not have the advanced capability that a switch did. When a switch first came out, the main difference between a hub and a switch was that it had a forwarding database. It kept track of MAC addresses at layer 2 and said, if a packet comes in on interface 1 and it's destined for a MAC address, and I'm keeping track of MAC addresses, and I see that MAC address is over on port 4, I'm only going to send that packet out port 4. I'm not going to send it out to everybody else. So now the overhead or the burden of all the systems on that local LAN having to stop what they're doing and taking a packet and read to see if it's for them when it's not, has gone away and has made basically the network a little bit more efficient. We all know switches today have gotten a lot more advanced. In fact, we call it a layer 3 switch today. There's really no such thing as a layer 3 switch. A switch is still a layer 2 device. A router is a layer 3 device. It's just all they've done is logically in the operating system combined the layer 3 functions and the layer 2 functions in one piece of hardware and one running operating system. It still does layer 2 functions and it still does layer 3 functions. There is no such thing as a switch that is layer 3. It's a switch that has a routing capabilities at layer 3. If that makes sense. But the term is stuck forever. So layer 3 switches are out there now. And in fact, switches when they first came out did not have the ability to do virtual LANing or creating virtual LANs within the switch. So just like a hub, all ports were on a single LAN, or what we would call a broadcast domain. We'll talk about that in a minute. Switches have the ability to carve up the amount of interfaces you wanted to have in a logical or virtual LANs or logical or virtual broadcast domains. So you could isolate traffic even more in switches as they became more advanced. But the first ones that came out didn't have that capability. They were simply a single LAN. They just kept track of what MAC addresses were on each interface, and they did that in a forwarding database. And that's what a switch's forwarding database is and what it's for and how it helps us improve network functionality over the old technologies like hubs. You all should understand the functionality of the ARP protocol. This is Address Resolution Protocol. Now, on any F5 exam, we really don't go into questions like, what does ARP stand for? That's not the kind of questions you're going to see on our exams. What F5 expects, and this applies for all of the layers of the OSI model and all protocols, is not that you understand what ARP stands for, that you understand how ARP works. And if you understand how ARP works, then apply it to the problems we're facing or the things that are coming up and happening on our network and how we can use tools around those protocols to solve problems. So understanding that ARP, what ARP does for us is it's a layer 2 based protocol that helps us link layer 2 MAC addresses to layer 3 IP addresses. So it sort of spans a layer 2 to layer 3 function of letting an operating system correlate a MAC address physically on the wire to an IP address at layer 3. But it is a layer 2 based protocol. A lot of times you'll be reading on the internet or in documents and even the study guides and stuff that are out there, and you might hear the term, it's a layer 2.5 protocol. There is no such thing as 2.5. I could back up to section 101 and you could see the OSI model has 1, 2, 3, 4, 5, 6, and 7. It does not have a 2.5. But ARP does straddle that 2 to 3 section because of the fact that it correlates layer 2 MAC addresses to layer 3 IP addresses. The way ARP works is if a system is running ARP, which almost all do, even routers run ARP, if host A wants to talk to host B out on the wire and it doesn't currently know the MAC address of host B, it may ARP for host B if it knows the IP of host B and says, I know the IP I need to get to, and it's on my local broadcast subnet. Meaning, if the IP address that host A is trying to get to for host B is not on the same local broadcast subnet, IP range-wise, host A will not ARP for host B because he knows that he has to send that packet to his default gateway to be routed to host B because they're not on the same subnet. But if they are on the same IP subnet, that means they will be in the same broadcast range. And if that's the case, then that allows host A to then send out an ARP request to looking for host B, basically. And what it looks like is an ARP who has the IP address of host B that he knows tell host A his IP address. And the MAC address it's destined for so that the switch can process and move it is an all Fs MAC address, meaning technically it's a broadcast. So remember I told you that a switch will not take in a packet headed for a MAC address and send it out all ports anymore because hubs used to do that and switches don't. But when a packet comes in with the MAC address of all Fs, that tells the switch this is a broadcast packet. I must send it out all interfaces. So an ARP request will go out to a broadcast MAC of all Fs so that the switch will send it out all ports. And when the systems get it, they will all stop what they're doing and they will look at the packet and say, is this for my MAC address? And every one of them will say it is. Because if it's for a broadcast, it's for everyone. So everybody will take in that packet and say, yes, it's for my MAC address, and hand it up to layer 3 of the OSI model. And they will take that packet then and say, is this for my IP address? And if they don't have 10.128.10.6 as an IP address, they will just throw it away. But if that one person that does, hopefully it's only one, will say, oh, this is for me, I need to tell 10.68 what my MAC address is. So he will reply, an ARP reply that his IP address is at his MAC address. And so then when host A gets that packet back, as a unicast back to host A, not everybody will get that one. Host A will then put that entry in his ARP table saying, now I know this IP address is this MAC address. So then they can have conversations without having to go to their router and be routed because it's on the local broadcast subnet. So that's basically what ARP does and how it works at a high level. And I know you've probably already read up on it and you know all about it, but thought I'd give you a little explanation there. You guys should understand the functionality and purposes of a broadcast domain. So what a broadcast domain is how far that all Fs packet or a packet destined for another node, how far a broadcast packet, base packet, will travel within your network. So this green circle that you see here, this really is, if you were to look at this network diagram on a test, and you don't see any IP space here, but you do see things like broadcast domains and collision domains. This is a layer 2 based diagram, right? A layer 3 would have an overlay of IP addresses on it, and maybe a layer 2 would have MAC addresses on it, but we don't really usually track MAC addresses all that much. We trust that they're unique to the nodes, even though they can have duplicates out there by the manufacturers. But basically, this is a layer 2 based diagram showing how far a broadcast based packet would travel within your network. And notice that the border device that separates the broadcast domain from the rest of the network is a router. So routers are our border-based device for broadcast domains, meaning typically broadcast packets do not travel past routers as they traverse your network. Unless that router has been manually configured by the administrator to forward broadcast packets, it will not. They will stop there at the router. The router will not send them on any further. But everywhere in the layer 2 based devices that are all connected together, broadcasts will travel. As you can see here, there is a switch diagram with 2 nodes hanging off of it, and that's inside with separate collision domains on each interface of the switch. And then there is a whole other collision domain that has a hub in it. And notice that all devices hanging off that hub are in the same collision domain, because the way hubs work and the way switches work, they don't isolate the traffic. So switches isolate the traffic down to the port. Hubs do not. They're all broadcasts go out every port, so collision domains are larger. But basically what we're talking about here is that in that layer 2 environment hanging off that router, a broadcast packet would traverse between all 4 of those devices freely, of the nodes, plus the actual network-based devices as well. But the router would not send them on. In this diagram, you should notice that it looks a whole lot like a standard layer 3 diagram. If we were to put IP addresses on this subnet and say this is the 192.168.1.1 or 1.0 subnet / 24-bit mask, and each device on there would have a 192.168.1 IP address, based IP address. So the way we've been building networks is the same way we've been doing it since the 90s. Layer 2 sets the structure, layer 3 overlays the layer 2. But that doesn't mean that it has to be that way. This is just best practice in the way we have always done things. But you could have, and these 4 nodes that are in this broadcast domain could be on separate IP subnets within the same broadcast domain. Meaning, if I put the 2 nodes that are on the left-hand side of the diagram in the 10.10.10 space with IP addresses, and I put the 2 nodes on the right-hand side of that broadcast domain in the 192.168.1 subnet IP range, the 2 on the left could talk to each other, and the 2 on the right could talk to each other freely via broadcast, because they don't have to go to their router to get to each other. But because the guys in the 10.10 are not in the 192 space, they would not ARP for each other, because ARP would say the IP range is not in my local IP subnet range, so I'm not going to ARP for you, even though they're within an ARPable broadcast domain. So they would say, hey, from any one of the guys in the 10 space would say, hey, I need to go to the router to be able to see if I can get to these 192.168.1 subnet IP nodes on the wire, even though they're in the same broadcast domain. And some people would say, hey, well, that's secure because those 2 systems can't talk to each other, even though they're on the same wire, same broadcast domain, a layer 2 network. Not true, because you could go into each operating system and add a secondary IP address. Like you could go into ones on the left that are in the 10.10.10 space and say, I need a secondary IP in the 192.168.1 space, and then they would ARP for each other and could talk to each other. There'd be no restrictions. But if you wanted to be able to control systems talking to each other, a router could simply be that control point, right? Because you could put ACLs on routers and allow routers to start to block traffic or permit traffic where you want them to. Don't necessarily have to have firewalls between broadcast domains within your network. But that's starting to get into a layer 3 discussion, which is our next objective, and we'll talk about that when the time comes. Hopefully this has been helpful.